In this video, we're going to talk about mirrors. Plane mirrors, concave mirrors, convex mirrors, applications of mirrors, ray tracing diagrams, the mirror equation, and the magnification equation. Let's start out by looking at some applications of mirrors. We might study mirrors because we want to study solar arrays. Solar arrays sometimes use mirrors to converge light. For personal care, you might use a mirror for shaving or for makeup. Mirrors are used for security purposes or to see around corners for safe driving in parking garages, for instance. Mirrors are used in cars and also in optical devices like cameras. So a lot of important uses for mirrors. Let's take a look at some of the simulations that we're going to explore in this video. So one fun simulation is going to take this, this candle that you see here, and we can look at the image of the candle from this mirror over here. Notice this is a curved mirror. This is called a concave mirror. As we move the candle back and forth, notice that the image, which is represented as the smaller candle over here, the image could get bigger, or smaller, and it could change location as well. And something very special happens if we move the candle very close to the mirror. We see that the image becomes very much bigger. So we're going to take a look at all the different calculations that go into predicting the location of the image and also the height of the image. Another simulation that we might look at is for convex mirrors. So if we change the location of an object in front of a convex mirror, notice that the image, which is behind the mirror, called a virtual image, is going to change location and change height as well. So these are some fun applications that we're going to look at with our simulations, but let's get right down to our notes for this topic. So in this topic, we want to start out by looking at the plane mirror. Very simple mirror, it's a flat mirror. And when we talk about the plane mirror, we're really talking about the law of reflection. So imagine that we have a flat mirror. So here's a flat mirror right here. Very simple. And you might ask yourself, if a light ray came upon this mirror, so this represents a light ray right here, you might think of it like a laser beam. If a light ray comes in and hits this mirror, how would you expect it to reflect off the mirror? Well, if you predicted that it's going to reflect at exactly the same angle, you'd be 100% right. Now, the way that we think about this is we imagine an imaginary dotted line called the normal. The normal is perpendicular to the plane of the mirror. So here we go. I'm going to go ahead and I'm going to draw a dotted line perpendicular to the plane of the mirror, and I call that the normal. And remember, in physics and math, the word normal means perpendicular. So if the angle coming in is theta I, and I got to tell you that theta I stands for incident angle. And the word incident in the context of optics means coming in. So the angle of the light coming in and then going out, that's a reflected ray. So this is theta R. And if you predicted that theta R, which is the reflected angle, is going to be equal to theta I, then you'd be exactly right. That is, in fact, the law of reflection. The law of reflection states that the incident angle theta I is equal to the reflected angle theta R, which is very intuitive, and you probably knew that already, but this is the law of reflection. All right, that's all we really have to say about plane mirrors, so let's move ahead to something more interesting. And a more interesting mirror that we might be interested in is called the concave mirror. Concave mirror has another name, sometimes called a converging mirror. And what a concave mirror does is it causes light rays to converge. So let me give you some examples and some applications of concave mirrors in everyday life. So our applications could include car headlights, satellite dishes, shaving or makeup mirrors, and acoustic mirrors, also known as whisper walls. Let's move ahead and take a look at our notes for concave mirrors. So when we do diagrams for concave mirrors, we need a ruler. Okay, so please grab yourself a ruler, grab yourself a straight edge, because otherwise we're going to have a really difficult time. Let's start out by drawing a diagram. In our diagram, we're going to start out with what's known as a principal axis. It's kind of like an x-axis, which we're going to draw like this. Okay, and let's label this the principal axis. All right, and then we're going to start with an object. Now the object could be anything, but we tend to draw as our objects an upwards arrow. So this right here will represent our object. So if you want to label this as object, that's fine. It could be a person, it could be an elephant, it could be a tree, it could be anything. Okay? Now, a concave mirror is going to be bowed away from the object. So the concave mirror that we're going to look at here is going to look like this. Now, I've tried to draw that as an arc of a circle because in reality, this is considered to be a concave spherical mirror. And these are the types of mirrors that we're going to look at, concave spherical, which means that this little arc was part of a larger circle. And if it's part of a larger circle, then that means that there was a center of that circle somewhere. And the center of that circle we're going to label wherever you think it is. I think it's about here somewhere. We're going to label that C. And C is going to be equal to the center of curvature. Okay? Now, there's another very important characteristic of these spherical mirrors. All spheres, like all circles, have a radius. And so this distance from the center of curvature to the mirror itself is going to be called the radius r. So r is going to be equal to the radius. And the radius could be in meters, it's often in centimeters, but the unit really doesn't matter in this case. So we have our center of curvature, and another very important point that we have to look at is called the focus. Okay? The focus is exactly halfway from the center of curvature to the mirror itself. So somewhere in between, we're going to label this capital F, and the distance from the focus to the plane of the mirror is called the focal length, lowercase f. So notice there's a lot going on here, right? We got capital C as the center of curvature, we got capital F is the focus, also called the focal point, and the lowercase f is called the focal length. And the focal length, again, is the distance from the mirror to the focus. All right, so we're really getting there. We've got a lot going on here. Let's consider that in this diagram, now that we've defined everything, we actually have to draw another diagram because there's so much going on here that we really have to kind of clean this up and look at specifically what we need to find. We need to look at this object height. We're going to call this HO. HO is called the object height. And this distance from the object to the mirror is what we call DO, object distance. So let's see if I can fit that down here. DO is equal to the object distance. And that's the distance to the mirror. All right, so we're looking at a lot of different quantities here. And you're asking yourself, if you're given all this information, this is typically what you're given in a problem. What do you want to calculate? You want to find the following. You want to find the image location. We're going to call that DI. That's equal to image distance. Okay? Where's the image located? That's going to be the image distance. We also want to know what's the height of the image. HI, that's the image height. Another question that might be asked is find the magnification of the image. M, lowercase m, is called the magnification. And we'll talk about that shortly. Magnification. There we go. Now, in order to draw this image, we're going to have to do something called ray tracing. Because these problems will often ask us, find where the image is located, and we're going to have to draw the image. The way that we do ray tracing is by following these steps. We want to draw at least 2 of 3 rays. I'm going to show you how to draw these rays in a second, but for now I want to walk through what these different rays are. Let's start with the P ray. The P ray aims parallel to the principal axis and it reflects through the focus. Okay? The next ray is called the F ray. The F ray aims at the focus, F for focus, right? And it reflects parallel to the principal axis. And the C ray aims at the center of curvature. Okay? With at least 2 of 3 of these rays, you can draw the image, which is often what you have to do for these problems. You have to draw the image. Okay? So now that we have our ray tracing strategies, let's talk about our general strategy for attacking any mirror problem. The first step is to draw a diagram, exactly as we did before. Label the center of curvature, label the focus, draw the object, and then use a ruler to make sure that your diagram looks good. The second step is to draw the 3 rays that we're going to talk about. The P ray, the F ray, and the C ray. That's called ray tracing. Finally, we're going to sketch the image where the rays converge. So once you've drawn 2 of these rays, maybe all 3, but once you've drawn 2 of these rays, you can sketch the image where the rays converge. And then finally, you can solve the equation, solve the problem using the mirror equation. Okay? So these are our steps. This is our strategy. And now what we want to do is look at 5 cases of concave mirrors. To really understand what concave mirrors are capable of, we want to really look at these 5 cases. 5 cases, starting with case 1. Case 1 is where the object distance is greater than the radius of curvature. Check it out. So here is going to be our principal axis, just like that. And let's draw, to the best of our ability, the arc of a circle like this. This is our concave mirror. All right. We're going to label the center of curvature. Looks like it's about there somewhere. And then the focal point, F. Okay? Now, in this case 1, the object will be located further away from the mirror than the radius of curvature. So remember, the radius of curvature is from the center to the mirror itself. Okay? So let's draw this object far away, out here somewhere. Okay? This is going to be called the height of the object, HO. Okay? And it's located at a distance, DO. And notice that DO is greater than the radius of curvature, R. Okay? So, let's draw our rays. This is called ray tracing, right? The easiest ray to draw, is my favorite ray, is called the P ray. The P ray, again, aims parallel and it reflects through the focus. Okay? So if we start at the very top of our image and we draw a ray that aims parallel, that means parallel to the principal axis, we're going to have a ray. So let's see if we can draw a P ray. Look at that. Parallel to the principal axis, and again, it reflects through the focus. Okay? So it bounces off this curved surface, and when it bounces off the surface, it's going to reflect, according to the law of reflection, it's going to reflect through this focus, just like, ooh, let me grab the ruler. Do this properly, just like that. Okay? And let's label this the P ray. And again, P ray stands for parallel. Aims parallel, reflects through the focus. Okay? That's one ray. The next ray that we want to draw is called the F ray. The F ray, if we take a look here, aims at the focus and it reflects parallel to the principal axis. So, we're going to take our ruler, we're going to aim at the focus, which you see here, and we're going to reflect parallel to the principal axis, just like this. And this is our F ray, because it aims at the focus and it reflects parallel. All right, now we're golden. We've got 2 rays. with two rays, you can sketch the image. So ask yourself, where do these rays intersect? Right here. The rays intersect right there. So let's go ahead and we're going to draw the image. Okay? And we can label this HI, because that's the height of the image right there. So what can we say about this image? The image is smaller in height than the object. It's inverted, meaning it's upside down. And I want to show you one more thing. If I wanted to draw a C-ray, I don't have to. But if I want to draw a C-ray, check this out. The C-ray aims at the center of curvature. Watch this. If I take this ruler and I start at the top of my object and I aim at the center of curvature, do you see this? If I aim at the center of curvature and it hits the mirror, it's going to bounce back through the center of curvature, right? Bouncing right back, according to the law of reflection, right? Bouncing straight back. And when it bounces straight back, look at that! It goes right through the top of the image. Look at that. All three rays, the C ray, the P ray, and the F ray, together all converge at the same point, and that's the image, okay? So in green is the image right there. So what might we be given in this problem? Let's look at some sample givens that we might want to look at in this problem. All right, let's say we're given the radius of curvature, and let's say that's 8 centimeters. Let's say we're given the object distance, which again has to be bigger than the radius of curvature. That's going to be at 12 centimeters. And let's say we're given the height of the object, which happens to be, in this case, 2 centimeters. Okay? So let's say these are all our givens. What might we want to find? We might want to find the location of the image, the DI, the image distance. So DI equals question mark. We might want to find the height of the image, HI equals question mark, and we might want to find the magnification of the image, M equals question mark. All right, so let's take a look at how we would find these things. Well, the way that we would find them is with two very important equations. And let's use this space over here to write these equations. The first equation is the mirror equation. Now, I might derive the mirror equation in a separate video. It would take too long in this video, but it's really simple, just basic geometry. The mirror equation is 1 over the object distance plus 1 over the image distance equals 1 over the focal length. Okay? This is the mirror equation, and I'd like you to please put a rectangle around this and star it, because this is a big deal. Okay, we're going to use this for every single problem that we do with mirrors. All right. Another equation we have to look at is the magnification equation. So, magnification equation. All right, so magnification M is defined to be, when we want to define something, we use 3 lines instead of an equal sign. The magnification is defined to be the ratio of the image height to the object height. So the ratio of HI to HO is defined to be the magnification. Now this happens to also be equal to negative of the image distance divided by the object distance. Okay? So please put a rectangle around this and star it, because that's the definition of the magnification. Now the magnification is very, very intuitive. So for example, if the image height were double the object height, we would say 2 over 1, the ratio is 2, right? We would say the magnification is 2. If the image height were 8 times as big as the object height, we would say the ratio 8 to 1 is 8, so the magnification is 8. Magnification can also be a fraction. So if the magnification was 1/2, we would say that the image is 1/2 the size of the object. So the magnification is very, very intuitive. All right, let's use the mirror equation and the magnification equation to solve this problem. All right, so in our problem here, what are we given? We've got our R equals 8 centimeters. We've got the object distance is equal to 12 centimeters. We've got the object height is equal to 2 centimeters. Okay. The first thing we want to find is the image distance. All right, so how do we find the image distance? Let's look at the mirror equation. 1 over dO plus 1 over dI equals 1 over f. Let's make some substitutions. So 1 over 12 plus 1 over dI equals 1 over the focal length, and the focal length in this case is 4, right? 1 over the focal length is 4. Now, how do I know that the focal length is 4? If we go back to our original diagram, the focal length is always exactly 1/2 of the radius of curvature. So let's go ahead, let's write that down. If you didn't get a chance to write that earlier, the focal length is exactly equal to 1/2 of the radius of curvature. And that's a really important definition for concave spherical mirrors. So please make sure that you've got that written down. All right, so in this case we've got our focal length. I'll put this up in our givens here. Our radius of curvature is 8 centimeters, so the focal length is equal to 4 centimeters. All right, so let's solve this equation. So 1 over dI equals 1/4 minus 1/12. The common denominator is 12, so we have 3/12 minus 1/12 equals 2/12, and from that we can see, if we take the reciprocal here and the reciprocal here, we get the image distance is 12 over 2, or 6 centimeters. Okay, so if we go back to our diagram, does it make sense that this distance will be at 6 centimeters? Well, yeah, it kind of does make sense, because the focal length was 2 centimeters. I'm sorry, the focal length was 4 centimeters. The center of curvature was 8 centimeters. So is this between 4 and 8? Well, sure, yes. It is actually between 4 and 8. Now, was our diagram perfect? Not exactly, right? We're using marker here. It's not exactly perfect, but we see that it's in the ballpark of where it should be. Okay, so fantastic. We got the image distance. So let's go ahead and let's put a rectangle around this. Let's put a check mark and put a smiley face, because we found where the image is located. It's located at a distance of 6 centimeters from the mirror. All right, great. So what else do we want to find here? Let's find the magnification. Okay, to find the magnification of the image, let's set up the magnification equation. So I'm going to go ahead and I'm going to put a bit of a separation barrier here, and I'm going to set up the magnification equation. M equals HI over HO, which is equal to negative DI over DO. Okay, so we don't have the image height yet, but we do have the image distance and the object distance. So let's go ahead and say, okay, that means that the magnification is equal to negative of the image distance. The image distance, again, is 6. So negative 6 over the object distance was 12. So negative 6 over 12, or negative 1/2. Now, what does the negative mean? The negative means that this image is inverted. Inverted because negative. Whenever you have a negative magnification, that means that the image is inverted. What about the fraction? The fact that it's a fraction means it's 1/2 as large. Oops, ran out of space. That means that it's equal to 1/2 as large. Okay? Fantastic. Okay. Is that consistent with the diagram? Absolutely. Look at this. the image is inverted, it's upside down, and look, it's approximately exactly 1/2 of that original object height. So we did a fantastic job with our diagram, and our calculations confirm our diagram. Let's go ahead and just really quickly calculate the image height. So if we use the magnification equation, we can say the image height, HI, is equal to the magnification M times the object height. You guys all see that? If we move the object height to the other side by multiplying both sides by the object height, HI is going to be equal to M times HO. So this can be calculated as the magnification, which is negative 1/2, times the object height, which was 2 centimeters. So this is equal to negative 1 centimeter. All right, which makes sense, because if the original height of the object was 2 centimeters, negative 1/2 of that is negative 1 centimeter. Okay, we got it. And we have effectively solved this problem. All right, so that was case 1. Let's look at the next case, which is going to be case 2. But before we do that, I want to just jump over to our simulation real quick, because we have a fantastic simulation that will show us exactly this relationship. So if I move this object, hopefully you see this object here, at negative 12. If I move this object, which has a height of 2 centimeters and a location of negative 12, if I move it to this position, look at this. The image is at a magnification of negative 1/2, so it's inverted, and it's smaller by a factor of 1/2. And that's exactly what we predicted with our equations. Fantastic. Okay, let's jump over to our notes again, and let's look at case 2. So case 2 is going to occur when the object distance is exactly equal to the radius of curvature. So if we once again draw our principal axis, there we go. Let's draw our concave mirror, and let's draw our focal point F and our radius of curvature, or our center of curvature, C. And this isn't the best diagram, but it's okay. All right, and if we wanted to draw our object precisely located at the center of curvature, such that the object distance is equal to the radius of curvature, let's see what happens. So first of all, we have our P ray. Remember, the P ray aims parallel, and it reflects through the focal point, like this. Okay, this is our P ray. And then our focal ray, our F ray, is going to aim at the focal point, and it's going to reflect parallel. So this is going to be our F ray here. And look at this. Something very special occurs. Notice that the geometry of the situation predicts that this object height is going to be equal in magnitude to the image height, and the object distance should be the same as the image distance. Let's see if that's true based on the equations. So based on the equations, if we have the same givens, so the radius of curvature is 8 centimeters, in this case the object distance is also going to be 8 centimeters, the focal length is going to be 4 centimeters. If we know all this, let's find the image distance. So 1 over dO plus 1 over di equals 1 over f. That's our mirror equation. So 1 over 8 plus 1 over di equals 1 over 4. And if we solve this for 1 over di, we get 1 over di equals 1 over 4 minus 1 over 8, which is 1/8. And we get, of course, di is equal to 8 centimeters, which is what we predicted based on our diagram, that the image distance would be exactly equal to the radius of curvature, which is the location of the object. Fantastic. Okay, what about the magnification? So if we use the magnification equation, M is equal to HI over HO equals negative DI over DO. And we can substitute now di was 8, so negative 8 over the object distance was 8, or negative 1. And that's exactly what we see. Same magnitude of height, but it's inverted, which is predicted by the magnification equals negative 1. Fantastic. Okay, let's move on to case 3. So case 3 is another interesting case where the object distance is going to be greater than the focal length, but it's going to be less than the radius of curvature. Okay, so in this case, let's draw our picture. Let's get our ruler. Let's draw the principal axis. Here is our concave mirror. Okay, let's label our focal point F. Let's label the center of curvature C. Okay, and now we're going to place an object between the focal length and the radius of curvature. So we're going to put it right here. Okay, and we're going to see what happens. Let's start out with our P-ray. The P-ray aims parallel, and it's going to reflect through the focal point. Okay, so here is our P-ray, and let's label the F-ray. Alright, so we're at P-ray, and the F-ray is going to aim at the focal point, so it aims down here, and it's going to reflect parallel to the principal axis. Just like that, and this will be our F-ray. Alright, where do they intersect? They intersect way over here. This is going to be our image height. Okay, so our calculations should predict that the image is going to be further away than the object, should be inverted, and it looks like it should be magnified a little bit, because this image height looks a little bit bigger than that object height. We'll see if that's true. So let's start out with our givens. So we're going to keep everything the same. We're going to have the focal length equal to 4 centimeters. That means the radius of curvature is equal to 8 centimeters. But in this case, we're going to put the object at a DO of, let's make something up, let's call it 6 centimeters. Okay? And we want to find the same stuff. We want to find the image distance, we want to find the image height, and the magnification. Alright? So let's set up the mirror equation. So we know the equation so well at this point that we could just set it up. 1 over the object distance of 6 plus 1 over the image distance di equals 1 over the focal length 1/4. Okay, so that means 1 over di is equal to, oh, we ran out of room. 1 over di is equal to 1/4 minus 1/6. And if we find a common denominator maybe of 12, this is 3/12 minus 2/12 equals 1/12. And again, you don't have to use common denominators here. You could just do this with a calculator. I chose very easy numbers here, right? But the problems in your textbook might not be such easy numbers. You might want to use your calculator if you're not familiar with subtracting fractions. So we have 1/12, so that means that the image distance is equal to 12 centimeters, right? Reciprocal, 12 centimeters. That is awesome. Now, is that consistent with our diagram? Yes, because we predicted that the image would be beyond the center of curvature, because the center of curvature was located at a radius of 8 centimeters, right? So if that's 8 centimeters, yeah, it makes sense that we'd be beyond, okay? Now, is this diagram to scale? No, it's not perfect, but it's okay. All right, fantastic. So we got our di. Let's now find the magnification m. So according to the magnification equation, the magnification is equal to hi over, ho equals negative di over do. Okay. Well, we don't have hi yet, but we do have di and do. So we could say that m is equal to negative di is 12, so negative 12, over DO was 6, so this is negative 2. The negative, of course, means inverted, and the 2 means that it's double in size. Now, did I double this in size properly? No, and I can tell you why. If my mirror had been a proper arc of a circle, so I'm going to use a different color here. Let me use my orange. If I had done a proper arc of a circle, that would have come down a little bit further. The F-ray should have come down further. I'll use purple here. The F-ray should have come down further, and then when it reflected, it should have reflected over here. So my image height really ought to have been maybe somewhere over here. And this happens. When you're drawing these freehand, it's impossible to be perfect. You know, that's why we use computers to do our calculations and our diagramming for us. So it's normal to do a calculation and see that your diagram wasn't perfectly to scale. But our diagram did successfully predict that it was an inverted image. It did successfully predict that the DI was beyond the center of curvature, and it did successfully predict that it would be bigger. Now, it wasn't double as it should have been, but it is bigger. Let's use a computer now to do this a little bit more properly. Let's bounce over to our simulation. We're going to take our object, we're going to move it between the center of curvature and the focus to 6. Okay? So here is our center of curvature that you see here on the screen. Here is the focus that you see here on the screen. And the object is right between the focus and the center of curvature at 6 centimeters. Okay? Take a look. Here's our P ray. Here's our F ray. And look, exactly as we predicted, the image is twice as large, it's inverted, and it's further away than the center of curvature. So the computer obviously did a better job of drawing this than we did, but that's okay. All right, let's bounce back over to our notes, and this takes care of case 3. Let's now look at case 4, a very interesting case. And I bet you can predict what case 4 is going to look like. Case 4 is going to ask, what would happen if the object distance was equal to the focal length f? So let's use our straight edge or our ruler to draw the principal axis. I'll try to draw a better spherical mirror this time. Here we go. So that's okay. Something like that. Okay. So let's draw our focal point, capital F. We'll draw our center of curvature, capital C. And we're going to go ahead and put this object precisely at the focal point. Okay. Now a P ray is going to aim parallel and reflect through the focus like this. And drawing an F ray here is really challenging, if not impossible, so we're not going to try to draw an F ray. We're going to take advantage of something very interesting. At the location where the mirror crosses the principal axis, I think you'll agree that the plane of the mirror is perpendicular to the principal axis. You see what I mean? Where this spherical mirror crosses the principal axis, this plane, or the tangent to the mirror, is perpendicular to the principal axis, which means that we could take advantage of the law of reflection here, which is that if the ray hits this point on the mirror, it's going to bounce off at exactly the same angle that it came in. And if that happens, look at these rays. Will they ever converge at all? And the answer is actually no. These two rays are going to be parallel. So the rays of reflection are parallel, which means they never converge. there will be no point in space where these two rays ever converge. They never converge, which means we're going to get no image. Another way to state that is that the image will be infinitely large, so we won't actually be able to see it. So no image oops, that's not an N, infinitely large, and it's also going to be infinitely far away. Which means that if you are approaching a concave mirror, there will be a point when you're standing at the focus when you will go completely blurry. You won't be able to see anything because your image is infinitely large and you are infinitely far away from the mirror. Or your image is infinitely far away from the mirror at that point. So very interesting case there. And the math actually supports that. Because if we set up the mirror equation where we have 1 over, if we're located at the focal point, that means we're located at 4, plus 1 over the image distance is equal to 1 over 4. You can see here the 1/4 cancel. We get 1 over di equals 0. And the only way that that can be true is if di approaches infinity. And that's what we meant by saying that the object is infinitely far away. And we can also prove there that the object is infinitely large. Okay, I have a video from another teacher that I want to show you in a second that illustrates the image kind of disappearing at the focal point that I'll show you in just a second. But first, let's tackle case 5, which is the last case for concave mirrors. And case 5, as you can predict, is where the object distance is less than the focal length. So let's once again draw our principal axis, and we're going to sketch our mirror like that. It's okay. Let's draw, of course, our focal length, or our focal point F, our center of curvature C, and we're now going to put an object closer to the mirror than the focal point. So our object, let's say, will go here. Okay? This is going to be very interesting. So, let's go ahead and draw our P ray. So again, the P ray is going to aim parallel, and it's going to reflect through the focus. So here is our P ray. Okay? Now, if we tried to draw our F ray, we'd have a really hard time, wouldn't we? Because how do you draw a ray that goes through the focal point? It's not going to hit the mirror. So the way that we do this is we have to draw a ray that's collinear with the focal point. The word collinear means within the same line. So how do you draw a ray that hits the mirror and is collinear with the focal point? You do it like this. You start at the top of your object, and instead of drawing the ray towards the focal point, you draw the ray as if it were coming from the focal point, and you get this. So the ray is collinear, that's within the same line as the focal point, and it reflects parallel, just like an F ray. Okay, so here is our F ray, here's our P ray. Now, where do these rays converge? Do they converge in front of the mirror over here? No, they diverge in front of the mirror. However, they appear to converge somewhere behind the mirror. Here we're going to take our straight edge, and this is so cool. Check this out. We're going to take our straight edge, and we're going to draw a dotted line to show where the ray appears to be coming from. This P ray appears to be coming from behind the mirror. Same thing with this F ray. This F ray appears to be coming from behind the mirror, like that. So where do these two rays appear to converge? They appear to converge behind the mirror. And this is our image over here. So, according to the ray tracing diagram, the object height is smaller than the image height. In fact, the image height looks to be maybe double the size of the object height. and it looks to be behind the mirror. We got a lot to look at here. So, one thing I want to share with you, if we go back to case 3, go back to case 3 for a moment. I want to share with you a very important definition. I want to share with you the definition of a real image. Okay? So go back to case 3 for a second. A real image is an image where light rays actually converge. Okay? That means the light rays actually converge at a point in space. And we saw that here the light rays actually converge, just as they did in case 2. So in case 2, we also had a real image because the light rays actually converged. If we go back to case 1, we're also going to have a real image because the light rays actually converged. So make sure that you write down that a real image is an image where the light rays actually converge. The reason that this becomes so important is that in case 5, we're going to have something a little bit different. This is called an imaginary or a virtual image. This is an image where the light rays don't actually converge there. No light rays actually converge there. The image only appears to exist. So you'll see an image in the mirror, but no light rays are actually getting there. So the difference between a real image and an imaginary image is that a real image is where the light rays actually converge. So for our purposes, a real image occurred in cases 1, case 2, and case 3. In cases 1, 2, and 3, we had a real image. We didn't have any image in case 4, obviously. But now in case 5, no light rays actually converge there. So we're going to call this an imaginary or a virtual image. All right, very cool. Let's move ahead now and let's calculate exactly what is the height of this new image, where is the image located, and what's the magnification of this image. So our givens, in this case, are going to be the exact same givens that we had before. For example, the focal length will still be 4 centimeters. The center of curvature will still be 8 centimeters. The height of the object will still be 2 centimeters. But now we're going to switch things up. The object distance is now less than the focal length. So the object distance, let's arbitrarily choose a distance. We're going to make it at 2 centimeters. Okay. So if we set up the mirror equation, we can find the following. We want to find di equals question mark. We want to find the magnification equals question mark, and we want to find the image height equals question mark. So, using the mirror equation, we can write 1 over the object distance of 2 plus 1 over the image distance is equal to 1 over the focal length of 4. And if we solve this for di, we're going to get 1 over di equals 1 over 4 minus 1 over 2. And you can already see that 1/4 minus 1/2 is going to be a negative number. In fact, it's going to be negative 1/4. Again, if the numbers are more messy, use your calculator. But 1/4 minus 1/2 is very easily equal to negative 1/4. And that means that we can predict the image distance is going to be negative 4 centimeters. Now, what the heck does this mean? A negative for an image distance means it's behind the mirror. Okay? So this object is located, or rather I should say the image is located behind the mirror. The negative means behind the mirror. Okay? So it's located 4 centimeters behind the mirror. And we can see that if this distance is 2, it makes plausible sense that this is a distance of 4. All right. So the next thing that we want to do is calculate the magnification. So the magnification, again, by definition, is hi over ho, or simply negative di over do, or negative 4, negative of a negative 4 right? Because it's negative of -4 over the object distance of 2. And this, oops, I lost you there, equals 2, right? Negative of -4 is +4 over 2 is 2. So the magnification is 2. Is that consistent with the diagram? Yes. The image height is double the object height, so yes, it makes sense that the magnification is going to be 2. It's a +2, which means it's upright. So the fact that this is a +2 means that it's an upright image. All right, and that's really cool. So the image height, obviously, will be double the original object height, or that'll be 2 times 2 centimeters equals 4 centimeters. All right. Whew. We did all of our cases there. Well done, everyone. Now I want to look at a simulation real quick, just to confirm these results. In the simulation, we're going to move the object closer than the focus. So here's the focus that you see over here. Here's the object that you see over here. And exactly as our calculations and our diagram predicted, the image is behind the mirror. It's imaginary because it's behind the mirror. The light rays don't actually converge there, but they appear to converge there. It's an upright image, and it's double the height of the object. Very, very cool. All right, the last thing I want to reward you with is a video, okay, from another teacher. So let me show this to you. He's going to have a pendulum. So what you see here in this video is a pendulum where there's a red ball on top with blue on the bottom, and he's got a concave mirror over here. Now he's holding it very close to the mirror, and he's going to let it go. So it's going to get further from the mirror and then close to the mirror. Further and then closer. Let's watch this real quick. All right, let's rewind that just a little bit. So what do we see there? Notice the image, when it's close to the mirror, is larger and it's upright, okay? But when it's further away from the mirror, it's smaller and it's inverted. You can actually see the colors of the image reverse. And also notice in the video that at the focal point, there's this moment where the image becomes so large that you can't really make it out. And that's when we have the object located at the focal point. So let's watch this maybe one more time. So you see here that the image is upright, and then it turns upside down. You see how the image there is upside down and it's getting smaller? And where is it? Right? It's hard to catch it. Right there. The image becomes infinitely large, and it actually becomes distorted for a second that you can't really see the image at all. So this was a very nice demonstration from this teacher who showed us the different aspects of concave mirrors. Okay, good news is that the convex mirrors will take us just a few more minutes, because there aren't a bunch of cases for convex mirrors. There's only one case for convex mirrors. So let's go ahead, let's jump back to our notes, and let's take a look at a convex or a diverging mirror. Okay? A convex or diverging mirror is a mirror that causes light rays to diverge. Okay? And one thing I want to share with you about convex mirrors right off the bat, okay, is that the focal length f is always negative for a convex mirror. And the rule of thumb for distances with mirrors can be summarized as follows. If a distance is behind the mirror, it's negative. So just like we saw in the previous example where we had the image behind the mirror, that had a negative image distance. And so if this focal point, as it's going to be for this diverging mirror, is behind the mirror, that is going to be a negative distance. So the rule of thumb, if a distance is behind the mirror, it's negative. The focal length is always negative for a convex mirror because, as you'll see, the focal length is behind the mirror. Okay, so let's look at an example of a convex or a diverging mirror. All right, here we go. We're going to start out with our principal axis, like always. All right, and whereas the bulge was outwards or away from the object. For a diverging mirror, the bulge is going to be toward the object. So watch this. I'm going to sketch this the best I can. Yep, that's not bad. So notice the bulge is toward the object. So here's our object over here. Okay, the bulge is toward the object. And look, the center of this circle, if this was a full circle, the center of this circle would be maybe somewhere over here, right? So there's our center of curvature. This will be our focal point F right there. All right, so now we're golden. Let's draw our rays. Let's start with our P ray that aims parallel. So this ray is going to aim parallel like this. It's going to reflect through the focus. Now it's going to have to reflect collinear with the focus, which means if it hits the mirror here, collinear with the focus means it's going to bounce off the mirror in this direction here. This is our P ray, because it aims parallel and it bounces off collinear with the focus. All right. Now, while we're looking at the P ray, it might be interesting to see where this ray appears to be coming from. So we're going to kind of go backwards with a dotted line to show where the ray appears to be coming from. All right. Now let's do our F ray. So the F ray is going to aim at the focus. The focus is now opposite the plane of the mirror, and we're going to reflect parallel. So starting at the top of our object, we're going to aim at the focus, but the light can't go through the mirror, so it's got to reflect off the mirror parallel to the principal axis. And this is our F ray, because it aimed at the focus and it reflected parallel. Now, where does this ray appear to be coming from? If we trace this ray backwards, this ray appears to be coming from this direction here. So where do the two rays converge? The two rays appear to converge behind the mirror. And that little green arrow represents where the rays appear to converge. Now if you drew a C-ray, notice the top of the image is collinear with the center of curvature and the top of the object. So that's absolutely consistent. We're not going to draw it because it may be too messy, but this does a fantastic job of predicting where the object is going to be and the height of the object. So let's go ahead and apply the mirror equation. Let's go over our givens real quick. So our givens, in this case, I think I chose some different numbers. Yep. So our radius of curvature, we're going to make it 10 centimeters. Switch it up a little bit. The focal length, again, we said that the focal length is always negative for convex mirrors. This is a convex mirror. So the focal length is going to be half of 10, so 5, but negative 5 centimeters. Okay? So, all right, what else we know? The object distance, we're going to say is, in this case, let's say 8 centimeters. And maybe the height of the object, we're going to make that, what did I say? I guess it doesn't really matter. Oh, I didn't say anything. I'll just make it up. Let's make it 4 centimeters for the height of the object. Okay. So let's apply. What do we want to find? Right? These are our givens. What do we want to find? Let's find the same stuff. Let's find the image distance, the magnification, and let's find the image height. All right, so let's apply the mirror equation. So 1 over the object distance is 8, plus 1 over the image distance di equals 1 over negative 5 is the focal length. So solving for 1 over di, we get negative 1/5 minus 1/8. If it were me and I was taking a test, I would put this in the calculator unless I really wanted to do the fractions. But it does so happen that the common denominator here is not too bad. It's 40. So negative 8/40 minus 5/40 equals negative 13/40. So that means that di is equal to negative 40 over 13, which I calculated to be negative 3.08 centimeters. Now, does that make sense? Well, the focal length was -5. Does it make sense that the image distance is less than -5? Yes. So if this is 5, it makes sense that this distance has a magnitude of less than 5, or 3.08. Looks perfect. Okay, so this image distance looks good. What else can we say? Can we calculate the magnification of this image? Certainly. So I can move this over here, and we can say, or I'm going to create a little bit of space over here. So the magnification, M, is equal to HI over HO, or negative DI over DO. And so that's going to become negative. DI was negative 3.08 divided by the object distance of 8 centimeters. A negative of a negative is a positive. So this is going to become positive 3.08 over 8, which calculates to 0.385 for the magnification. Now notice, it's positive. What does that mean? It's upright. The image is upright. But the image magnification is less than 1. Less than 1 means that it's smaller than the object. Okay? All right, and then from here, if we really wanted to, we could calculate the image height very easily. The image height is going to be equal to the magnification times the object height. Right, you get that from this equation up here. HI equals M times HO. So we get 0.385 times the object height. We made up a number of 4 centimeters. So 0.385 times 4. And what are we going to get? I actually need to grab my calculator, which is hiding. And my calculator states that we get 0.385 times 4 equals 1.54. So the new image height will be 1.54 centimeters, which of course is less than the original object height of 4 centimeters. All right, now this pattern that we saw here for the diverging mirror will be the same regardless of the location and the height of this image. I can show that to you, or with this object. I can show that to you with this simulation. So let me pull up a very cool simulation. Here we have a diverging mirror, or a convex mirror, and if we change the location of the object, notice all that's happening is that the height of the image is changing and the location of the image is changing. But notice the image is always smaller and it's always upright. And that's going to be a nice property of convex spherical mirrors, is that the image is always smaller and it's always upright. So convex mirrors are great for making big objects appear smaller. So for example, your rear view mirrors on your cars may be convex mirrors because it might take something very large and make it smaller for you to see. And that's why you see on the mirrors sometimes it says objects in the mirror may be closer than they appear. All right, so that covers, if we go back to our notes really quick, that covers everything that we need to know about diverging and converging mirrors. So good luck, and I'll see you next time.